Hi, I'm Matt Manassi, application engineer for the TI's integrated signal chain, here to talk to you this morning about our ultrasound EVM with the TDC1000 and our level and fluid identification test cell. Before we get into the EVM, let's talk briefly about ultrasound and time-of-flight measurements. The TDC1000 allows us to do time-of-flight measurements using ultrasound. But let's go real quickly through what that time-of-flight measurement entails. The TDC1000 drives a piezoelectric transducer, which takes an electrical signal and turns it into a mechanical pulse. That pulse then transfers through the material until it reaches an acoustic boundary. That acoustic boundary is defined as any place where there's two different speeds of sound of materials. Now, at that boundary, some energy transfers through the boundary and some is reflected back. The TDC1000 is going to let you detect and digitize that echo as it comes back to the transducer. Looking further on this slide, here's an overview of what we're looking at. A microprocessor connected to the TDC1000 would create a trigger pulse. The TDC1000 then would create a start pulse as a synchronization, as well as the excitation pulses to the transducer. The echo, as it transfers back, will be received by the TDC1000 and digitized, forming this wave here. Now that we understand how to do time-of-flight calculations, let's look at some applications where this is used. The first application is level measurement. Most importantly, with the TDC1000, we enable a non-invasive level measurement, where I can mount the transducer outside the container. This is useful in situations where the fluids are highly caustic. Note the TDC1000 analog front end is hooked up directly to an MSP430 microprocessor. The interface is entirely digital. Once I've done my time-of-flight calculation, I now know my speed of sound from my material. I can then determine the level of that material in that tank. This non-invasive technique, where I'm mounting the transducers outside the container, can be used in a variety of container materials: metal, glass, or plastic. Another application for the TDC1000's time-of-flight measurement capability is fluid identification. Fluid identification is done the same way as level, where I have a transducer outside my container shooting to either an adjacent wall or a target. That time-of-flight calculation is fed into this equation. My distance, in this case, is known between my transducer and my target. Feeding that into the equation here allows me to determine the speed of sound of my medium. This is useful for identifying materials without actually having to touch them. This is accomplished using the TDC1000 and a stopwatch function. That stopwatch function will need to be determined by the differences of speeds of sound of the materials you're trying to measure. That can be anywhere from microseconds to nanoseconds, depending on those materials. Now that we've gone through the applications for the TDC1000, let's go over the chip and see how it accomplishes this analog processing. The TDC1000 allows us to do this analog processing with such a high level of integration because within it is all the pieces necessary to excite and detect echoes coming from ultrasonic transducers. That's achieved by having a configurable transmission chain, a configurable receive chain, as well as configurable stop pulse generation. When I say configurable, I mean they are fully configurable by any microprocessor via the SPI interface. Now that we've gone through the ultrasound overview, let's look at the demo with the TDC1000 EVM and level and fluid identification test cell. Let's go over the EVM first. Here I have the TDC1000 analog front end. Here is the TDC7200 digital stopwatch. Here we have the MSP430 supervisory processor and serial to USB interface. Now let's go over and look at the test cell. Here we have the fluid identification and level test cell. The test cell is equipped with two 1 megahertz piezoelectric transducers. The one on the side allows us to do fluid identification measurements. The one on the bottom allows us to do level measurements from the bottom of the container up to the top. Let's go back to the GUI to load the configurations to run the demo. In the GUI, there's multiple tabs across the top of the screen. For this demonstration, we'll be focusing on the TDC1000 tab and the Graph tab. From the TDC1000 tab, you have access to all of the registers within the TDC1000. For this demonstration, we're going to load pre-configured registers that are set up to interface to this demonstration. We do that using the Load and Save Config registers in the lower right-hand side of the demo. By pressing the Load Config button, that opens a window that accesses what files I can then load. We're going to load the level demonstration first. While those register values are loading and updating user settings, what we're looking for at the bottom of that interaction is that load config successful. Now let's go to the oscilloscope to see what's happening at the TDC1000. On our oscilloscope, we have three traces. A yellow trace, the start signal, the pink trace, the stop signal, and the blue trace, which is the echo. The TDC1000 creates the start pulse after it excites the transducer. It amplifies and filters the echo, and from that creates the stop pulse. Now that we've seen what's going on the scope, let's go back to the GUI and take those time of flight measurements. We do that by going to the TDC1000 Graph tab. On the Graph tab, this tab allows us to gather data and perform some statistics on those data. The statistics are assembled over a programmable number of samples. In this case, we start grabbing data once the Start Graph button is pressed. Here we notice the time of flight initially is about 25 microseconds. As we add water to that, that number will increase. Let's do that now. As we reach the top of the cell, we get to the upper limit of the cell, which is 160 microseconds. Other features on the graph are the capability to expand how we view the data. You can copy the data to an Excel spreadsheet, you can clear the data, or you can zoom out to capture all the data you've had all session long. Now we've seen the TDC1000 level demonstration, let's use the same system to do a fluid identification demonstration. I still have the water in my container, which I need to empty out, so let's do that now. I haven't emptied it all out. I've only emptied it down to about 100 milliliters. Now in this test, I'm going to try to add alcohol, isopropyl alcohol, a few drops to this volume of water and easily detect it. To do that, I've got to go back to the TDC1000 tab and reset those registers. Again, here we're going to use the Load Config button to load the concentration or fluid identification register values. And most importantly, we can see that this configuration was loaded successfully. Going back to our Graph tab, we need to erase the previous data that's there, possibly. Use Clear Chart to erase previous data. For our fluid identification, first we need to grab a time of flight baseline before we add our alcohol. Let's do that now. We've grabbed about 25 samples. Here we see our baseline average, and there's our standard deviation. Now let's add the alcohol and see how it affects our time of flight. Adding 2 drops of alcohol, stirring the solution, and let's start taking our samples. Immediately, we can see that for 2 drops of alcohol, I'm seeing a 40 nanosecond change in time of flight. That's significant. That change in time of flight will depend on what those materials are, and that's the key for using fluid identification. Here's a good website for identifying different speeds of sounds of various materials: rubbers, solids, liquids, gases. I use this website very often. In today's video, we went over how to use the TDC1000 EVM and its fluid identification and level test cell. If you have more questions about this, go to ti.com/ultrasonic. And thanks for watching.